We can start it in the bootloader. We go into the source and we will create a new file, which I can name, for example, driver spi.c. And what put as API functions, we can borrow it from the middleware, from the external memory manager, and here from the user there is the template file which is defined as a week, and we can copy all the content from this file and put it into our SPI driver and save it, of course. And we will remove all these weak functions and we will start to define them. Okay, so now the API will look like this. Because in the driver these functions are defined as a weak, we can redefine them here on this place. Before we start implementing the function, I will bring here into our file some more variables. One of those will be the XSPI handle, and I will simply, here my variables, I will define it as an external. And to be sure that I don't need to rename everything like this, I will name it simply as a XSPI. And also I will define one return variable and a timeout, which will be very helpful during debugging and implementation. The return variable to see what is the return from the function, the timeout in case that I will use the timeout number in this project. And I think I'm missing two things. One is the page size and the sector size, which will be also used during my programming. So we can save it and we can continue. If you look into the datasheet from the external memory, you discover that every memory have defined command set. Some of them can have the same command set, and it can be different from for the SPI mode and, for example, for the Octo SPI mode. Because we are now using only the SPI mode, we will focus on the command set which is related to the SPI mode, and you need to select the commands which are important for us. I like to start with the simpler commands and go into the more difficult commands, and also this will help us to first debug the application as soon as possible to see if we can read, if we can send commands, if we can get something from the memory. What I like to do is first to start with the reset command to be sure that the memory is in the default state. Then go to the read ID command to see if we can read something from the memory, so this will validate our communication. Then we can continue with the standard read command for the data, so we will read the data. Then we need to learn to read the status register of the memory. In case that we will start the programming or the erasing, we need to learn how to read this status register. Then we need to learn how to write the configuration, because the memory by default they are locked, and if you want to do the erasing or the programming, you need to unlock them, so you need to write the configuration into the memory to unlock it. Then it's usually good to learn how to mass erase. It's much simpler because you don't need to send any address. And then more difficult commands, which is the program, where we need to send the data, and also the sector arrays, where we need to calculate which pages will be, or the sectors will be erased. I recommend to start first in the SPI mode to try it on the simpler scale, and after that, after you have this part working, to move into the double data rate, the DTR mode, or to switch on into the Octo SPI mode. because in case of the flash, you can always do this into the simple mode and, for example, switch to the DTR and OSPI only for the reading, which can also make things a little bit simpler for us. So we will start with the first commands, which will be part of the init sequences. So it will be implemented in our init function. And first we want to reset the memory. So we will use the reset enable command, which must be followed by the reset command. So the command for the reset enable, it's usually by the number 66. It's the 8-bit command on the one line. It have no data. The reset, it's the 99. And then I would like to try if I can read the ID. So I will see if I am able to read the data from the microcontroller with the command 9F. The commands are described inside the datasheet. So all this information you need to check with the datasheet, but the most of the memories have very similar commands. Now, how the commands are sent? It's possible to use two options. One is, we can say, manual, and second one is automatic. First is called the indirect mode, which is the state of the XSPI after the reset. When you use the HAL functions to trigger the transmit or the receive of the data and sending and the reception of the commands. So here is the user always in control. And there is the memory map mode, the execution in place, when you switch the XSPI into this mode, and then the memory is visible as the internal space of the microcontroller. So every read from the DMA or the core, it's automatically trigger the transmit into the memory. So he will automatically send the command and do the reading of the writing. We basically use the both modes. The memory map mode we use when the API asks us to enable it, and the indirect mode we use for the sending all the commands. The sending the commands in the indirect mode is quite simple. We will always call the HL XSPI command, which can be followed with the transmit in case that we want to send the data, or by the receive if we want to receive the data from the memory, or if we want to send only the command without any data, it is not followed by anything, so the command is only function which we need. And to send the command, we need to tell him what we want to send. In this case, when we're using the command, we need to give him the information inside the command structure, and we need to fill this structure. This structure is unfortunately quite big, so I always propose to start pre-fill it at the beginning to create something like the template, and then to use it for every command and only fill the necessary changes or the parameters which we want. And we know the first command, it will be the reset enable followed by the reset, so this will be first two commands. And we can start to preparing them. So the command is usually sent by the HL underscore XSPI underscore command. We will fill the HSPI 1. Then he wants the command structure and the timeout. So we will fill the timeout value and the command structure. If you don't know which type it is, you can mark the function and press S3, and we can simply here take the command type, which in our case it will be constant and it will be definition of the function. I can put it inside the brackets to make it a little bit nicer for me. And now we need to fill the command parameters. So if you again mark the type and press F3, you will see that there is a lot of parameters, And in case that you don't know where to start, if you have the line, there is usually the definition or the comment, and there you can see where is this type defined. So if you search for this part, you will find all the possible options which are possible. They are still in the header file, so they are local. And those will be the options which we can fill. This you can do for all the parameters. I will try to make it a little bit faster and explain you what these parameters are doing and why you need to fill them and what they will mean. Now I can put here the parameters which I copied before. Okay, I can remove the comments, and here I will put the same name. Command, here will be the person, here small c. Okay, so now it fits, and now we will talk about the parameters which will be constant, because most of those parameters will be always constant for us, so we don't need to bother them, and only few of them we need to change for the different commands. Now I can look into first command element, which is the operation type. The operation type corresponds with the modes of the XSPI. We have basically two operation types. One is the indirect mode, when all the commands or the operations which the SPI do, it's triggered by the user, by the library. And there is the memory map mode, where the XSPI automatically sends the commands, and internal memory space of the microcontroller, it's used when we want to read or write. It's automatically translated by the XSPI into the memory. For this reason, we need by this operation mode tell the XSPI which operations or the commands will be used for the reading and for the writing. In this case, the operation type for the indirect mode, it's the common operation mode. And for the memory map mode, we need to send one command which will tell him how to do the read from the memory, and the second command to telling him how to write into the memory. And after that, it's possible to use the memory map mode. Now we can add the modes. So for the most of the time, I will use this common mode, and I will put here as a note the other two modes which will be used for the memory map mode, which will be the mode for the read, and also for the write. Oh, it's not the wrong button. Sorry, for the write. Okay. And the second parameter is the IO selection. The IO selection allows us to select which pins of the port will be physically used for the transmit and receive. In case that you're using only quad SPI, you can select that it will be the lower ones, the ones in the middle, or the ones at the end. In case that you have octal mode, you can select that it will be the lower pins or it will be the higher pins. Of course, for the octal mode, all the pins will be used. So this will be selected inside this IO selection. In our case, the memory is connected into the lower pins from the 0 to the 7. From the 0 to the 7, so this will be mode which we will want to select. In our case, it will be pins from the 0 to 7, and it will be again the constant for the most of the commands, so there will be no comment. The next part will be modes. The modes and the parts related to the sending and receiving the data. In this part, we need to fill how the command will look like and all the operation, which parts it will use. We can divide this transaction or this command operation into multiple stages. First is that the command informations. It usually consists with the mode, the instruction which we want to send, the width of the operation, and if we will use the double data rate, then will be sent the address. So again, we use the mode, send the address, the width, and the double data rate. Then we can alternatively send the more bytes because some memories allow that. In our case, we will not use this feature. Again, we will send the mode, bytes, width, and the double data rate. Optionally, the number of the dummy cycles. Usually for the writing, you're not using the dummy cycles, mainly for the reading. And at the end, the format of the data. What is the mode, the length of the data, and if the dual data route is used, and the data strobing, if it's used or not. And we can start with the first parts, which will be the modes. The modes are usually common. Every operation or the stage have them. So I will only talk about the modes, and we will set them all the modes in the same time. The mode. The mode is telling us how many bits we will use for the sending or the receiving the address, data, or the commands. It's starting from the 1 bit. It's possible dual, so we use the 2 wires, we will use the 4 wires, 8 or 16. In case that you will select the 1-bit mode, using only 1 wire at a time, but it's working as a standard legacy SPI. So 1 wire is the MOOC, which sending data into the memory, and 1 it's acting as a MISO. In case that you will select the dual data or more, quad, octo, hexa, the data pins are bidirectional. So the same pair is used for the sending the data, and the same pair is used for the receiving data. The modes, we can select the mode for the instruction phase, for the command phase, for the address phase, for the alternate byte phase, and for the data phase. You can select if you want to use the command or not. You all have always possibility here to decide if the command will be sent or address if will not be sent. So in our case, the first command which we want to do, it's reset. So in this case, only the command will be used, and the rest of this part will be said that we don't want to send it at all. Now I can start to filling the modes. So first I will start with the instruction. The instruction, it's need to be sent every time. So I will send that the instruction will be sent over 1 line because it's the SPI mode. The second part, it's about the address mode. The address mode can be optional. Sometimes I want to send it, sometimes not. In our case, when we will use the reset, we don't want to send it, so the address mode will be none. And I will put here as a comment the second possibility which I have, which is to use the 1 line. The next is the alternate bytes. This is always none on this memory. So none, it will be fixed, it will never change. And the last part is to the mode for the data, which is also none in this case, in this reset, because if you remember, we will not expecting any data. In case that we want to expect data, we will put there the 1 line. And this is the mode. Now we can skip maybe the instruction. This we will fill at the end. I think we will continue with the width, which is again the same for the instruction phase, address phase, alternate phase, and also for the data phase, not phase because we sending the data as a bytes. The width. The width is defining us how many bits the operation will consist. In our case, most of this will be in the 8 bits because the command is the 8-bit, so this will be 8-bit. We have possibility to use the 16-bit, 24 or the 32. For the addressing, we mainly use the 32 because we have a 32-bit memory. So for the addressing it will be 32, for the commands it will be 8. So this mainly corresponds only for the instruction phase, for the commands, for the address, and for the alternate bits, but because we alternate not use, it will have no meaning for us. So we can fill this part, so we can fill this instruction part. The instruction width will be 8 bits always, no exceptions. The address phase will be also always 32 bit. In case that we set here none, this value have no meaning and will be not used, but in case we will use here 1 byte, this value will have the meaning, so we can keep it here. We don't need to put there 0 or something like that. And for the alternate bytes width, we again put the 8-bit to put there something meaningful. We can briefly mention the length. When the length, it's defining us how many data bytes we want to send. In case that we set the data mode into 1 byte or more, the length will start to have meaning. This will be important maybe when we will start to reading the ID. In our reset operations, it have no meaning now. So we will put there by default now 0. Next part is the DTR mode, when you can select if you are sending the data on the rising and also on the falling edge of the clock, or you sending them only on the rising edges or the falling edges, depends on the mode, which we were talking about these modes in the exercise number 1. In our case, we will not use the double data rate, because this needs to be enabled by the configuration, usually to write into the configuration register, so it's not there by default. And for this exercise, we will keep it on the normal single data rate. We will set all these double data rate modes into the none, so we will not use this mode at all. We can go into our configuration, and we will set the instruction double data rate mode into the disable. The same will go for the address. The same for the alternate bytes. And the same will be for the data stage. I'll put here the spaces to make it a little bit nicer. Okay, we can save it. The next is the DQS option. It's the data strobing signal. When on the very high speed memories, the signals are sometimes quite delayed. So when the memory receives the clock edge, it takes little time to send the data back, which can create the delay. But in case that the host is sampling on these edges, it can disturb the data. So there is the feedback signal from the memory. It's the opposite direction. And the memory is sending this signal into the XSPI to telling him now you can sample the data, which can effectively increase the compatible memories and increase also the frequency. In our case, it's mainly used in the dual data rate in the DTR mode, which is quite recommended to use this option. In our case, we're using the standard SPI, so we will not use this option and we will disable it. Now we can set the DQS into the disable. DQS mode into the disable, and we are left with the only few parameters. One are the context parameters, so mainly the instruction which we want to send. If we want to send any address, the alternate bytes, which will be part of the command. In case that you want to send the data itself will be sent by the transmit or receive the function. But because our first command is the reset, there are no data, so we will not use the transmit and receive function. And the last parameter which I'm also missing is the number of the dummy cycles. It depends on the command, and there is usually written inside the datasheet of the memory if you need to use the dummy cycles between the command and the address and the data. So we can fill the dummy cycles to 0 because we don't expect anything. The alternate bytes will be also 0 because we have nothing. The address, it's now also 0 because we want to send first this reset command, and the instruction is really important. So I created the instruction definition for the reset, and I will put it somewhere here to see it as a curl or the definition. And first will be this reset enable command. So we put here the reset enable command. And this all will fill the structure, and this XSPI command will send this reset enable into our memory. One thing which I am missing here is to put here the return variable in case that this will fail. I always like to see to show me if something happened or not. Now we sent one command. Now if we copy this structure, we can send the second command. I can maybe put it into the brackets to make it separated, to be simpler for the copying, and also to see the differences between the commands. I will copy here the structure too. Okay. To make it more clear for me. So with these two commands, I here need also to change the command for the reset because it will be second command. So this will be this one. So the first function will send the reset enable, second one will send the reset. Effectively, I now create this operation. So I send the command 66, and now I send the reset command 99. So now what I'm missing, I want to check if I can read from the memory to see if the communication is really working or not. So we will implement the read ID command. This I can do by copying this command. Okay, I can copy the command again. For sure, I will remove this part to not forget. Also, now I need to read the data. The data length should be 3 bytes. I want now to read the data, so I will comment this part, and I will use this one line because I will be now able to receive the data. And I need to define also my instruction for the read ID. So I will define here the ID, and the read ID should be 0x9f. So this will be the instruction which we will be sending. This part only send the command, but we need to receive the data somehow. So we will call the HL underscore XSPI underscore receive. Again, HXPI. This one. We will need to define the buffer, and we again use the timeout. This will be okay. And I will define here some buffer underscore T device ID, which will be 3 bytes big. And we can add it as a buffer. Again, check the return variable. Our project is prepared, so we have the reset commands, we have also the read ID command, so we can put here the breakpoint, and we can run the debug. because we have this inside the init function, there is nothing else to try. It should directly go into this function. We can step over and check the result of the function, and we see that content is the 85, 02 and the 00. So we can cross-check this with the documentation, and the value which we were expecting was the C2 89 39. So it seems that we have the issue somewhere. It can be that we send the command incorrectly, so it's always good to cross-check this configuration. The second possibility, which can be reasonable, is that we are running too fast and the connection between the microcontroller and memory it's not enough. So we can try it by going to the main, into the OSPI, and we will change the prescaler, and we will increase the prescaler to 1. So we will divide the frequency by 2. And now he probably compiling everything. It's not an issue. And I believe I can run the debug and cross-check if the value will be still the same or now it will be valid. So I can again run to the breakpoint, do the step, and check the content. And now is C2 81 39. So if I look inside the documentation, so we can see that it's C2 81 39. So it seems valid. So before we ran too fast. So I can try then change the frequency step by step and make it lower and lower, or I can check it by the oscilloscope. Do not forget, I will open my Cube MX, and here in the OSPI I simply change the parameter to not forget on this to prescaler to 1 to be sure when I configure it later. So now it seems that the reception is working. So we can implement more and more commands. We have now correct initialization sequence. So we enable the reset, we reset the memory, and then we do reading the ID, which is optional. Sometimes it's good to check that the read is working correctly. And in the rest of this function, we need to return the return parameter, and by default, the return is marked as an error. So I will change it here into something meaningful that we are okay. So this was initialized the init function. Then I propose to continue with the simpler parts, which will be the reading. We will not implement the read function because we have memory map device, so the read function is not needed. But what we need to do, we need to implement the function to enable the memory map mode and to disable the memory map mode. The simplest is to disable the memory map mode, where we only use the function HAL OSPI _ abort. Calling the function abort will stop the memory map mode in case that the memory map mode was running before. And now into the memory map mode. Before we can enable the memory map mode with the HL _ OSPI _ memory mapped. Sorry, there will be the configuration which I will use. The configuration, yeah, it's only about the timeouts. There is the structure for the memory map mode, the memory map configuration, which we can have here. And the structure have only two parameters, which is the timeout for the activation, which I will use the timeout, my default timeout value, and I will disable this feature. But before this, I can use this function, I need to tell him which commands or the instructions use for the read and for the write. So for this, I need to tell him these two commands. This I will do with the standard command procedure. I can borrow here the reset one, for example. and I will put it here. I will remove the parts which we don't need. The instruction, this will be our own. We will now use the address, so this part will be also gone. The operation type will be also different, so I will remove this. Otherwise the instruction will be one line mode, it will be still 8-bit. The address width will be 32, this is okay. No alternate bytes, so this is okay. And of course I need the data mode. I want to send the data, so this will be different. In this case, in memory map mode, the data length doesn't matter. The same is for the address, because the address will be automatically set by the memory map mode. So the address and the length of the data are irrelevant in case that the memory map mode is activated. So these parts I need to fill, and I will create the second copy which will be used for the write. So this part I can mark as a read, and this part will be for the write. Because I don't want to really write any information there, I can keep them completely the same. So this was maybe pointless. I can then copy this configuration, because we will not really write into the memory, because I will show you the writing is more complicated and it's not possible to do by one command. This is possible to do with the RAMs, with the flash it's unfortunately not possible. Now, what we need to fill there? The operation type is then for the read. It will be the type for the read. This is clear. And we need to discover the instruction. The address mode will be automatically 1 byte. I want also the data mode to be 1 byte. And what I forget, I need to fill the dummy cycles, because usually the read is crucial and the dummy cycles can vary based on the mode. So I need to check inside the datasheet from the memory. So let's look on this. I have here my slide with the informations from the datasheet. So I will use this fast read command, which will have the instruction 0C or the command 0C. Here require 4 byte address, which is my 32, so it will fit. And we need to pay attention, we need to send 8 clock cycles. If you set less, you will start reading the data before there are any valid data. In case that you set more, you lose some bytes which were already valid and you throw them out. So in our case, we need to set the 8C as an instruction and 8 clock cycles to the dummy cycles. So the dummy cycles will be then 8. And the instruction I can again create the define to make it readable for me later on. I can create the read here to have them together. This is my read, and even I have here the dummy cycles, so I can copy this part into my part. And when we enabling the memory map mode, do not forget this is my read, and this will be my dummy cycles. Do not forget, or allow me to change it fastly in case that I create the incorrect configuration. So this is configuration for the read. For the write, because I will not use it physically, I will simply change here the read to the write, and I will use the completely same configuration, because even if I send the command for the write, he cannot write because the memory is not unlocked. This is the difference between the flash and the RAM. On the RAM, usually one instruction is enough to allow to write into the memory. On the flashes, it's more complicated and you need to first unlock the memory. But because we don't want to write in the memory map mode now, this will be enough, because without calling this write operation type and sending the command, it will not allow us to switch into the memory map mode. And after this, the memory should be already functional and it should be possible to switch into the memory map mode, but I need here to return some valid return variable, to be sure that it will allow me to continue, so I will return the OK. And I believe we can build the code and we can try it. In case that we have already the application from the exercise number 1 still inside the external memory, we can try it and see if we can really see the content of the memory. I can then select the bootloader and I can enable the debug, start the debugging. He will not in this case download anything into the external memory because I'm debugging only the bootloader, which is completely inside the internal memory. And I can step over the code, and I want the place when he is starting use the external, sorry, I need to this one, when he start to enable memory mapping mode, which is inside the boot application function. Inside this, he is calling the map memory, which is the one which will enable the memory map mode. And here in this function, he will start using my function or my implementation to use the memory map mode, which will be here to enable memory map mode. And he will go over all these functions. And when he executes this one, the memory should be already mapped. So I can open the memory tab. I can put here the 90 million, and I should check if I have some valid data or not. The additional one, and I seem that I have the memory, but not the valid one, because I think this is my encrypted memory. So I will try to update the last one. Okay, I updated the memory because I forget that I tried before the exercise number 3, so I had there the wrong content. Now I did the same step, and if you look inside the memory and the additional one, you should see the content which was there before, which we created with the exercise 1, which was this toggling with the LED. And usually if you look on the code and the start of your application, any application, it's usually starting with the table called the NVIC table, which is the interrupt vector table where you have all the interrupts. And the first value, it's usually used at the start of the microcontroller, which is the initialization of the stack pointer, which should point into the RAM. So in this case, it's 20 million, which is our RAM. There is the vector for the reset function, which it's inside the external memory, and they are the other reset like the non-maskable interrupts and the hard fault. So this seems to be valid, so we can read successfully from the memory. So our implementation seems okay. In case that you have completely new memory, it's more tricky because it will be probably empty and you will not see anything. So to test that your reading is really working, we need to go in over the arrays into the programming to be able to test it fully. But in our case, because we already had something inside the external memory, we know that it's now working and we were able to validate this part. Next step, we can fill the one function, which is the support function, and it's the get memory address. And it's telling the external memory manager where to jump inside the external memory. In our case, we need to return him this base address. I assume it's the pointer. Yeah, it's the pointer. So we can remove this one, put it as a pointer, and we tell him that our memory it's on the starting on the address 90 million. And after this, the bootloader should be fully functional because he should be able to obtain the address where to jump, and he will jump it, so he will run the application inside the external memory. So if we try it again to download it and run it, then because we already have the code from the exercise 1 inside the external memory, you should be able to see the LED blinking. And okay, I can run it. I made one more mistake. I here not return the valid that everything is okay, so this needs to be return that it's okay or return 0, and so the abort function should return also that it's possible to abort. And this will be mainly used during the programming, so not now, but this one will be used in the bootloader. So now I can retry it and it should be okay. Okay, I run it, and now I see that my LED is blinking, and if I pause it in the stack pointer, I can see that I am inside the application. I didn't connect the application into the bootloader, so I cannot debug now the application. But for me, it's now the memory map is working. So now we can move to the erasing and the programming, which is more difficult topic. Now, the erasing of the memory. The most simpler from the erasing and the programming is probably the mass erase, because there we don't need to handle the addressing. Only what we need to tell him that we need to erase. Which for this we need to use this mass erase command, which I found in the datasheet. So erase chip, which is 60. There is no address, no alternate bytes, no dummy cycles, no data. However, you cannot send him simply this command, because he will not accept it. Inside the datasheet or for the most of the memories, you need to unlock the memory first, which means you need to call the command write enable. Sometimes the write enable are not set in the one clock cycle, because the memory can be busy doing the other stuff. So it's good to check the status of this bit by reading the status register, which all the memories have the status register, and we want to check this bit, the write enable latch, which telling us if this bit is set, we can write into the memory or read from the memory, program the memory, erase the memory, but we can manipulate it. After we send this mass erase command, this bit will be again automatically read, and for the next erase or any memory write or read, for the write operation, you need to set it again. So this will be in our case called periodically for the erases and for the programmings, this too. And after we initiate the erase, the memory start erasing, but we are not sure how long it will take. You can surely look into the datasheet of the memory and put the time there, fixed time, or you can simply check the status of the erasing in case that it's shorter. You will be notified, and for this we again use this read status, the same operation like here, but we will be checking the different bit, which is the write in progress. The write in progress means also the erase and the sector erase. So before we start to mass erasing, it would be beneficial for us to implement these functions to check us the states, because we will use them on the multiple occasions. So first I will implement the write enable, and then I will implement the read status to check if my memory write is enabled. And after that I can continue with the mass erase, and at the end I again implement the read status for the memory. I will implement this status reading as a function, so I will prepare here 3 local functions, because they will be used only in this file. To make it simpler for me, I will name it as a driver SPI write enable. Then the checking if the write was enabled, it will be write enabled, and the waiting function for the write complete or the erase complete will be called the write. So I can implement these functions, and I will start with the write enable, which is the simplest one. And I will again use the function from the reset enable, because it's the same a structure, only what is different will be the command. I will want only the instruction or the command. I will not send any address. I will not send any alternate bytes, and I will not send any data. If I will remind, I want only send the instruction or the command 06. This is all what I want to do. So I will define the write enable command to have it here. So write enable, and this should be all. So when I call this function, it should start enabling the write. I can implement now the function to check if my write was really enabled, because I am always not, I cannot be sure that maybe there was noise or something else. I will use the similar structure, but now I want to read the data, and I want to read the 1 byte, this status register, so it will be 1, and the data mode will be 1 line. So this will allow me to enable the reading of the data. When you have the none, it will not use this part of the code at all. And I need to implement the instruction, and if I look into my notes, so I enable the reading of the 1 byte, and I need to send the command 05 to reading the status register of the memory. So I will again define my status register, the 05, to have it somehow structured. So read status register, and I will put it here. And because I here now using also the data, the command is now not enough. I also need to use the read function. So I will use here the reading HAL XSPI underscore receive XSPI 1, the data and the timeout. The timeout I fill. For the data, I need to create the variable to be able to store it somewhere. So I will create the local variable in case that it's needed. So I can here status value. I can put it here, for example. So this will be my status value, and this is what I want to have back. And be careful, he requires to be a pointer because he expects that is buffer, and he will fill me only the lowest 8 bit. So I can in theory put it as a 8-bit, but I think 32 is okay on the 32-bit microcontroller. And this will read me the status. But sometimes it can happen that on the first read the status will be not yet set, so I can repeat this operation multiple times until the status is set. So I will put here my temporary variable. For example, I will call it wait, and I will set the wait to the 0. Sorry, I don't need the type. I will send it to wait, and I put here the while. Sorry, it's not a simple wait, it's use set it to wait. It's equal to 0, so 0 is equal to wait. So I will repeat this operation again and again until I can finish. And how to finish? I simply put here if, and I will check this value. If it's equal to the waiting mask, or I will mask it with the waiting bit, and If it's not equal to 0, I will set wait to 1. So he will stop waiting basically. And I forget to define this part. I need to define the bit from the status register, which I believe should be bit 1. So it will be variable value 002. I can define here both the states which I want to check in the future. So it will be 02 for the wait, and in case the write in progress, it will be 1. So this is now defined, and I should be able to see if the memory is unlocked. To be sure, I can rebuild my project to see if I made any mistakes. Seems not. Seems to be okay. I think he is complaining about the type that he wants to 8-bit pointer, but so far it should be okay. And I'm missing the return value. Yeah, I forget the return value. I can put here the return 0, for example, and I think here to return 0. Okay, I'm not checking the return variable so much, so it should be okay. Now we implemented these two functions, and I can implement also the third one to wait on the write in progress, because I can copy it mostly from the write enabled function. So I can take this all, I can put it here, because I'm sending the same command, because I still want to read the status register. So this don't change, it will be still 1 byte. But what will change is the bit which I want to check. It's not the val, but it will be the write in progress bit. So now this will handle for me to waiting when the write or the programming operation will finish. And if I have now this support functions, I can implement finally the erase operation or the mass erase operation. So I will again take the, for example, the reset enable command, and I will go into the mass erase. I put it here. And first, before I use this command, I will call this driver. First, I will call the driver write enable. And I forget, if I am here in the driver write enable, I want to put here the check if the write is enabled. Write enabled. Perfect. And I can put it like this to make it simpler a little bit. So when I call the write enable, I am sure that the memory is really enabled, which will be important for my programming. So here, this will unlock me the memory. So now I can execute the command for the erasing. So I need to create this command. Again, I will remove the instruction. We can check what is the erasing command, how it looks like. The mass erase is pretty simple, and I need to send him the 60, no data or no addresses, so it's quite simple. So I don't need to change anything here, only to implement this instruction command to tell him that I want to chip erase, and to make it closer I will put it just only here to make it closer to us. Later on I will move it on the top of the file. I will call the command because no data are there, so the erasing will start, and to be sure when the erasing finish I need to call driver write wait, when he will be waiting until the erase is completely done. Now we have the erase implemented. Now how to test it? We can simply test it that we put it into the init temporarily. So I will put it here into my init function, and I can try it if this will work. I can put it as a null because I have nothing there. I'm now not sure if he wants, no, he wants the small one, I believe, or 0. I think I can put there the pointer to 0 even, which should be okay because the pointer is not used anyway. But only I forget again to return this this valid return state. Okay, and we can try to build. We can run the debug, and it should now erase the mass erase, completely erase the external memory. And we know when he will start to use again the boot application, we should see that the memory will be empty, which will confirm to us that that it is working. I can put the breakpoint one here, and I can look inside. I can cross-check that it is working. First, he will send the write enable command. So now it is done. I can check the return variable, which is 0, which is valid. Now he will check the state. And here I can control what he returned, because on the first bit there should be 2. And in this case it's 2. If we compare it to the datasheet part, so here it's 1, which will give us the 2 inside the hexadecimal or decadec numbers, which seems that the memory is unlocked. So we can continue. He will tell him stop waiting, and he can proceed with the erasing. So he will erase the device. Seems the device was erased because we left the wait. And we can go into the boot of the application, the memory mapped. I think I forget that I put there the breakpoint, and we can look into the memory. And you see that the memory is completely empty. So it seems our mass erase it's working perfectly, because he erased everything what he could. The next step, because we can erase, it's maybe a good place to start the programming, and we can now try to program the memory. The programming will be very similar to the erasing or the mass erase, with the one difference. The write enable must be also there. The read of the status will be also there, so this part will be copy paste, and also the last status when we checking if the programming is done. So this we can completely copy the mass erase or the chips erase function. What will be different will be the write. When we need to use the different command, of course, we also need to use the address. And then we need to tell him what the data which he needs to program. So in this case, the data will be from the 1 to 256. This will depend on the function parameter which we have there. So the best way how to start is to simply copy the mass erase, and we will change only the command and also add one more feature, because it's possible that the code will want us to program even more than 256. In this case, we need to call this multiple times, so there will be loop to check if we need to repeat it again and again. But for the first step, I recommend to do it only once to check if you can at least program the address 90 million or 0 in this case. For the programming then, we can take the mass erase part. I can copy it, I believe, completely. This one. And I will locate the write. So the unlocking will be here. What will be the different will be the instruction. Also, I want now to use the address. The address will be then filled here. And I also want to use the data. So the data will be here. For the programming, it's not necessary to set the dummy cycles. Always cross-check with the manual, but for the most, the memory which I know there is for the writing, it's not necessary to set any dummy cycles. And the data length will also depend on the size of the data. The memory requires the length to be from the 1 to the 256, but we need now also pay attention in case that he wants to program more. We need to split the writes, so there will be more logic behind. And of course, because we're using now the data, we need also to send the data into the memory. So I will prepare here this one, and I use the HL XSPI underscore transmit, again this part. The data I'm still not sure what will be my buffer, and the timeout will be the same. Now first we need to fill the instruction. This is usually the straightforward part, so I will put it again on the top. So this will be my instruction, the page program. But I need to add the more logic for the writing. So I will define 3 helping functions. One will be my address offset to control if I program everything into the memory. There will be the current the address which I want to program and the current size of programming. So this size I can use here. The data length will be this size, and the program address will be this part. But I need to somehow evaluate, and first I will create the loop to program until I run out of the data which I was supposed to program in this case. So I will repeat it until everything will be programmed into the memory. Okay. And the condition will be in case that my programming offset is smaller than the size which is the input, I will program. I will run the programming again and again. So first I need to check the program address, or set the program address, and the program address will be the address. Here now you need to be careful because the address sometimes it's inside the STM32 address space, which is 90 million. However, the memory requires the address from the 0. The external memory don't care about 90 million. For him, the memory is starting from the 0. So we need to mask this part with the mask, and we want to remove this 90 million. And I think I defined here my memory mask. No, not yet. So I will define my memory mask in this case to be able to mask the addresses which are above the range of the memory. So this will be my memory mask. So I will mask it with the address. So in this case, he will change the 90 million to the 0. So instead of the 90 million 1, it will be 1. And now I need to also add into this address, the address offset. And this will give me the real value. So if the address will be 90 million, it will be changed with this to 0, plus the offset at the beginning is 0, so I will program first the address 0. So this is valid. Now the size. It's possible that the size will be bigger than the 256, and my limit for the calling of this one programming, it's 256. So I need to do the check, so it will be if, and it will have also else. So if my size is smaller than the offset, plus page size, I know that the size will be the rest of the buffer. In case that it will be bigger, I will go into the else, and I know that my programming size will be equal to the page size. Because this is the maximum, the page size will be maximum which I can program, and I believe I defined the page size here. Yeah, it's 256. In case that is smaller, it's very simple. We will evaluate the size. The page size is then size minus the address offset, so it will be the rest of the size which is left. So this will define me the size which I want to program. And the last part which I forget, it's to evaluate the pointer. So it will be pointer, and I will need to put there the address. It's the data. I think it's the data plus the program address offset. And this is all what I needed. I will put the semicolon. He will do the programming, he will do the weighting, and after the programming I need to increment again this offset, because now I programmed usually the page size. It's the maximum. I assume that I will not program something less. And at the end, when the size will be smaller, it will be the last time, so I will leave this loop anyway. Or I can use the program size to make it more clear. And that's it. So this will be used for the programming, and seems that this will be all what I need. Now, to be sure that it's working, we can again test it with the same way how we test the mass arrays. Don't forget then to remove this mass arrays when you will work normally with it. And we can use this right, and I can put it manually something there. The first will be 0 argument, because it's the pointer of the object which we are not using. Then the address I will put again 0, so I will program effectively the 0 or the 90 million in this case. The data, I need to put the pointer into some valid data. So I will put the data from the beginning of our flash memory, which will be the uint8_t pointer, and it will be 0x08001234. This one. This is our flash when this bootloader is located, so we can compare it then later on if the values are the same, and we can put 256. And again, I think I fill everything here. Yeah, the return variable, it's okay, and we can check if this will work. I can put 512 to see if I can program even the bigger buffers. I can run the debug. Don't forget, if you want to write into the memory, the part of the memory needs to be always erased first. So if I switch first the programming and then the erasing, it will probably not work, because he is not able to rewrite the memory again. Okay, I left the function, so I can go into the memory map mode. Sorry, I forgot to put there the breakpoint. When I use the memory map mode, sorry, inside the driver, the memory map enable here. So programming mass arrays, programming memory map mode, and I can check the memory map, and it seems that it's not programmed yet. Okay, so I will check what is wrong. I know now what is wrong. It was my mistake when we used the function write wait. We were waiting for the write in progress, but I forget here we need to change the condition, because when the write in progress it's 1, the memory is programming, but we want to end the sequence when the write in progress is back to the 0. So it was my mistake. So I expect in this case it will then work as we expected. Okay, we can start the debug again with this fixed of this byte. We can run the mass arrays. Now it will take the appropriate time. It's not so fast because of the size of the memory, so be patient. Definitely it's the reason why to implement the sector arrays and not erase everything. We do then the write and then the memory mapping, and you can see that now we have the RAM and then the content of the flash seems so. We can compare it by the address which we use for the testing, the 0800 and 4 zeros. And if I can set the same view, you can see that these two areas will be identical. So it seems that my programming is working. So only last function is needed to be implemented, which is the arrays, the sector arrays. To not erase everything, but only the sectors. Again, don't forget to remove this one when you don't want to work normally with this, because otherwise it will erase all the time your memory. Now we are missing the sector arrays. So how the sector arrays looks like? It will be again very similar to the mass arrays or the program. So the write enable, reading the status of the write of the progress, but the sector arrays is a combination between the page program and the chip arrays. We need to send the command and only the address of the sector which we want to erase. This is all what we want to do. So let's implement it. For this, I think the best way is to start with the mass arrays. So I will copy here all the content of the mass arrays. And we will put it into the sector arrays part. We will remove the instruction because the instruction will be again different. And now we will also use the address. So I want the address to be 1 bit. We will not use the data, so this command it's okay. Again, it will be write, so no dummy cycles. So only what I need to do is to set the correct command for the erasing. So let me search for the sector erase command. It should be this 21. This sector arrays instruction. And now again, what I'm getting is the address where I should start to erase and the size what I need to erase. So again, it will be wrapped inside the loop because it's possible that I need to erase multiple locations, not only one. So I will create the helping variable, the erase address, which I will set at the beginning for the address, and I will do the while. I will wrap it around all the programming. Okay. And I will wait until I will do it until my write address is smaller or equal than the original address plus size. The address and the size we giving from the programmer or from the user, and they should be always aligned with the sectors from the memory, because the loader will know this. So he will always add to us the aligned address. In case that you plan to use it in your code and you worrying that you will put here not aligned address, you should always align it into the sectors which are defined inside the memory. I think here we have 4 kilobyte sectors. So this address needs to be always divided by the 4K. If not, you need to divide it by yourself or return error that you cannot erase this area because it will erase the different area than you wanted. And okay, we erase this address. After the erasing, I think the last part what we need to do is to increment again the erase address with the sector size, which I believe I defined too. We can check that the sector size, yeah, sector size is defined too. And this should do for us the erasing of the sectors. We can test it again. Okay, I put here the program because I know the program is working. I will put here only 256 because I will erase only one sector. I will put here the 0 for the first. I think the first is the address, which will be again the 0, and the 426 will be the size of the sector. I think it's valid. Yeah. I can again compile it. Okay, I can remove this one. It should be now much faster because I'm not erasing the complete 32 megabyte. And I can switch into the memory map mode. Probably I will see the same thing, but I see that now it was definitely erased because before it was program 512. So for me, it seems it's working. Now, this was for the bootloader. I think we implemented all the functions which we needed. Only thing what I will do, I will remove this the main testing arrays and the program because this will be not here in the final code. So you can remove it. And we can move into the external loader because all this, it's now implemented, how the loader wants it. We don't want to use the init because we will use the execution in place. So this has no meaning. The read will be also not used because we have the reading as a memory mapped. And everything is used except the get info, which is also not used in this case. So we can simply take this file, the file which we have here, and simply we can copy it inside the external loader. So we can simply take it and we can put it into the external loader.